Hey friends, welcome. Today we are going to discuss Bose Einstein statistics. And Bose Einstein statistics generally they are applicable to those particles having integral spin, or we can say the spin is integer. So, for example, the particles like we have hydrogen, we have deuterium, then we have nitrogen, and we have photons. So these particles they follow Bose Einstein statistics, and hence these particles are also known as bosons. As we know that the name comes from the Bose or Satyendranath Bose, who is very famous scientist of Indian community. So Bose and Einstein they together gave this statistics. Or when we were deriving a Boltzmann distribution statistics, at that time we have considered that all the particles are distinguishable. That means if I change the position of any of the particle, a new microstate or a new microstate will arise and there will be a new complexion. But in case of Bose-Einstein statistics, we are considering that the particles are indistinguishable. Now, when the particles are indistinguishable, then at that time, when we change the position of the particle, then also no new energy levels or no new microstate will arise. Suppose any particle is sitting in energy level 1, and if I take that particle and put it in energy level 5, 10, 15, any energy level, as the particles are identical, no change in the microstate would arise. Okay, and hence there won't be any complexion in the system. Now suppose if we are considering that we are having ni number of particles in a system with energy ei, and again over here also, as we have considered in our Boltzmann statistics, the total number of the particles are constant, and as well as the total energy of the system is constant. So we have ni number of particles, and that ni particles are distributed amongst ei energy state. Okay, the ei energy levels, and these energy levels are also degenerate. Okay, so these energy levels are also degenerate. That means that these energy levels they are further divided, or they are further subdivided into energy levels having, or they are further subdivided into similar energy levels. So these energy levels or these states are represented by gi, or gi over here it is also known as statistical weight factor. Let me explain the degeneracy. Suppose if I am having any energy level, say E2, so in this energy level there are further 3 more levels, like I can arrange 112, then I can arrange 212, 211, and I can arrange 1 to 1. So the energies or all the 3 states are same and the energy is same. So over here for energy level E2 the degeneracy is 3. So any energy level, or if any energy level is subdivided into same or different levels having almost equal energy, then those energies are called statistical weight factor, or it is the degeneracy of that particular energy level. And what is the amount of degeneracy? It is given by the statistical weight factor gi. So over here every energy level has certain amount of degeneracy, and that amount of degeneracy it is given by gi. Now we need to fill different particles in different energy. Suppose we start with, suppose in energy level E0 our degeneracy is G0, and we are putting N0 number of particles. Similarly in energy level E1 whose degeneracy is G1, we are putting N1 particle. Similarly energy level E2 having degeneracy G2, we are substituting N2 particle, and so on. We move up to EI energy level whose degeneracy is Gi, and in that we are putting Ni number of particles. Okay, so now in order to put Ni number of particles into Gi energy level, we will require Gi minus 1 sections. That means let me explain by giving one example. That is, suppose I am having a box like that, and if I want to make 4 equal partitions, then I have to draw 3 lines. That is, when I draw 3 lines, or if I put 3 partitions, then I will get 4 equal divisions. So similarly, we take this example, that is energy level E2 is divided into 3 states. So in order to achieve these three states, we need to make two partitions. So when we make two partitions, we get three states. So we have total energy level, and that energy level is to be divided into Gi amount of states. So the total partition will be Gi minus 1. Okay, so now the problem comes is that we need to distribute Ni amount of particle into this Gi minus 1 amount of partitions, or the total Gi state, and that will be given by, we will have Ni plus Gi minus 1 factorial. So this is the combination in which, or this is the combination by which we can put Ni number of particles into this particular partitions, or this much amount of energy levels. And also we know that there are Ni number of particles, and that has to be distributed between between Gi minus 1 partitions, and we know that the particles are indistinguishable. So there will be permutation of this particle and this states amongst themselves also. So the actual number by which we can distribute Ni number of particles between Gi state is given by Ni Gi minus 1 factorial upon, we will have Ni factorial into Gi minus 1 factorial. So this permutation will give us our thermodynamic probability, or it will give us the distribution of Ni particles among Gi states. So we can write thermodynamic probability W is equal to, so this is for our ith energy level. So similarly for 0 energy level, or for G0, we can write N0 G0 minus 1 upon N0 factorial G0 minus 1 factorial. Similarly for energy state E1, E2 and so on can be written, and hence we can write for N0 N0 plus G0 minus 1 factorial upon N0 factorial G0 minus 1 factorial into, we can write N1 plus G1 minus 1 factorial upon N1 factorial G1 minus 1 factorial, and dot 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 into, we can write Ni plus Gi minus 1 factorial upon Ni factorial into Gi minus 1 factorial. Okay, now again we know that the multiplication, or as we write for sum we write summation, for multiplication it is represented by capital pi, and hence we can write capital pi into Ni plus Gi minus 1 factorial upon Ni factorial Gi minus 1 factorial. So now we want to find out the most probable distribution, and for most probable distribution what we will do is we will take ln, or now what we need is we need to find the conditions for most probable distribution, and in order to find the condition for most probable distribution, we can evaluate this term by taking ln on both hand side, because ln will be an easier factor for us to solve. So we will take ln on both hand sides, and hence we will have ln of W is equal to, and again we know that ln of multiplication is a addition function, and hence this pi will be converted into summation. So I can write directly summation, take ln, so it will be, I will put it into bracket, so we will have ln of Ni plus Gi minus 1 factorial minus, and again it is division, so it will be minus of ln of Ni factorial minus ln of Gi minus 1 factorial. Now what we will do is we will apply Stirling's approximation to this term, and we know the Stirling's approximation, that is if we have ln of x factorial, then that can be written as x ln x minus x. So this is our Stirling's approximation, and this Stirling's approximation we will use in this equation as well as in this equation. And also the value of 1 or the value of unity is negligible as compared to the value of Ni and Gi, because Ni plus Gi will be a very huge value, as we know that for us in a single mole of any compound also there are large number of particles. So as compared to those large number of particles, unity is very small value. That is, for 1 mole of any compound, say we have 6.023 into 10 raised to 23 molecules or to 10 raised to 23 particles. So 1 is very less, and hence we can omit this one. And again, as compared to Gi, 1 is very small value. So hence from here also the unity can be omitted or the unity can be neglected. So we will apply Stirling's approximation and we will neglect unity in both the terms, and hence we will have summation. This will be Ni plus Gi ln of Ni plus Gi minus Ni plus Gi minus Ni ln Ni plus Ni. Then we have minus Gi ln Gi plus Gi. Now we have minus Ni minus Gi, and over here we have plus Ni and plus Gi. So these terms will be cancelled out, and hence we will have summation Ni plus Gi ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. So we have this much terms remaining. As we have discussed in the Boltzmann distribution law, that is, for most probable distribution, the value of ln W will be equal to 0, because when we are considering most probable distribution, the most probable distribution, we will have only a single microstate. That is, only single microstate exists for a most probable distribution, and the probability is so high for that distribution that rest all the states are neglected, or rest all the states are very low as compared to that most probable distribution. And hence for most probable distribution, the value of thermodynamic probability is constant, or say it can be unity. That is, we have only a single most probable distribution and it is unity. And when we differentiate this, that is when we take d ln of W, then that will be equal to 0. Okay, so what we will do is we will differentiate this relation also. So we will differentiate this relation, and I can directly write it as summation. Both these terms we can differentiate by using the formula of differentiation by parts. So I can write it in square bracket. We will differentiate this first, and after that this. So differentiation of Ni, we can write it as dNi. Gi is constant, so it will be 0, and into this term as it is. So we can write Ni plus Gi. Okay, again plus, then we will have this term will be constant. So Ni plus Gi, and differentiation of ln of Ni will be 1 upon ln of Ni plus Gi, and again this term will be differentiated, so we will have dNi. Again, now this is over, then we have minus of, again we will differentiate Ni, so it will be dNi ln Ni, and minus minus again minus, so Ni into differentiation of Ni will be 1 upon Ni into dNi, and these terms are nothing but this is constant, Gi is constant, so whole this term will be equal to 0, or this term, differentiation of this particular term will be equal to 0, so we are not differentiating it. So again over here both these terms will be cancelled out. We will have minus dNi, and both these terms will be cancelled out, and we will have plus dNi. So again plus dNi minus dNi will be cancelled out, and hence we will have the term that is summation ln ni plus gi into dni minus ln ni dni, and that is equal to 0. Okay, because both these terms cancel out, we have only plus dni. Both these terms cancel out, we will have only minus dni, so it will be cancel out plus dni minus dni, and hence we will have only this much left, and hence as this term is equal to dlnw and dlnw is equal to 0, we can equate it to 0. Further, what we can do is we can take dni common, and as we know that subtraction is a division function, we will have summation of ln ni plus gi upon ni and into dni, and that will be equal to 0. This is our relation for most probable distribution. Now again, we know that as the number of particles in the system is constant, we can write summation of ni, or summation of ni can be written equal to n, that is total number of particles, and if we differentiate this, then we can write summation of dni will be equal to 0. And similarly, the total energy of the system is also constant, so we can write summation of ei dni is also equal to 0. So this is, suppose this is our equation number 1, equation number 2, and equation number 3. So these are the three equations. So we will apply Lagrange's method of undetermined multiplier, and what we will do is we will multiply this by alpha, this by beta. We will add both this and subtract from this, because we can add also, but when we subtract it, the result comes good, and it is mathematically easier. So we will subtract it, and hence we will add, say we will do minus 1 plus 2 plus 3, and that will be equal to 0 by using Lagrange's method of undetermined multiplier, and hence we will have summation minus of summation, that is ln ni. I can divide ni by ni, so it will be 1 plus gi upon ni, so I can write 1 plus gi upon ni into dni plus alpha summation dni plus beta summation ei dni, and that is equal to 0. And again we can subtract summation one side and dni another side, so we will have summation of, I can write alpha plus beta ei minus ln of 1 plus gi upon ni and into di, and this will be equal to 0. Now further, as we know that the dni, that is change in number, or dni is not equal to 0. So dni is not equal to 0. So in order to make this relation equal to 0, the bracket term should be equal to 0. Now how dni is not equal to 0? Let me explain you that suppose we are having different energy levels, and dni, that means the change of particles, or we are changing the number of particles. Okay, so we know that the total number of particles are same, or the total number of particles remain constant, but what we can do is, from I can take 5 particles from energy level 1, and I can put 2 particles in energy level 4, 2 particles in energy level 5, and 1 particle in energy level 6. Okay, so over here what is the change? That is the total sum, that is summation dni is equal to 0, because the total change, it remains 0, because and 5 particles will be, or the 5 particles are subtracting from energy level 1, energy level 2, and those are added in different energy levels. Okay, so the total sum of the particles or the sum of the change in the particles is always 0. Okay, but the individual change, suppose I write change of particle, that is, I can write dn1 or dn2 or dn3. So this change is a finite term, because suppose if in energy level 1, if I am picking out 5 particles, so this will become -5, and of that I am substituting say 3 particles in this and 2 particles in this, so it will be +3 and +2. So those change for individual particles on individual energy level is a finite term, and hence this dni cannot be equal to 0. Oh yes, their sum will be equal to 0, but their sum, suppose if we take this sum, so the sum of dn1 plus dn2 plus dn3, it is equal to 0. But for individual or for as dn1 dn2 and all the changes in the number of particles, they are independent of each other, what will happen, this is not equal to 0. So over here this term is not equal to 0, and hence in order to make this relation equal to 0, the terms which are written in our square bracket, it should be equal to 0. Okay, so hence this square bracket terms is equal to 0, and hence we can write alpha plus beta ei minus ln of 1 plus, let's break it over here, so 1 plus I have gi upon ni, and that is equal to 0. So we can now directly use simple mathematics of rearranging this, and when we rearrange this, we will have ln of 1 plus gi upon ni is equal to alpha plus beta ai, and again if I want to remove ln, then this will we can take antilog, or it will become e to the power, and hence I can write 1 plus gi upon ni is equal to e to the power alpha plus beta ei, and then I can take 1 on that side, so I can write gi upon ni will be equal to e raised to alpha plus beta ei minus 1, or I can rearrange this equation in the form of ni by gi, because ultimately we are interested in ni by gi. So ni by gi I can write it as 1 upon e raised to alpha into e raised to say beta ei minus 1 also. So this relation is known as Boltzmann Einstein distribution law. One more modification can be made, that is gi can be taken on that side, and hence I can write ni will be equal to gi upon e raised to alpha into e raised to beta ei minus 1, and this is our final relation which gives us the distribution of ni number of particles amongst gi energy level, and all those particles which follow this particular distribution pattern, those particles are known as bosons. This is our Bose Einstein statistical derivation, and these are the final form. Hope the derivation was clear. Thank you very much.